We are here with simple harmonic motion, which is a special type of a periodic motion. And it follows the law that the restoring force is directly proportional to its displacement, and this displacement is towards the position of equilibrium. Alright, so a classic example of a system revolving or oscillating in simple harmonic motion would be a simple pendulum over here. As you can see, this is the bob of the simple pendulum, and the restoring force is acting on this direction as the simple pendulum is going towards this direction to make its displacement. So a simple pendulum is an ideal example of a system going through simple harmonic motion. Okay, so let's get into the mathematics of a simple harmonic motion. So, as you can see, simple harmonic motion follows the notion that F is directly proportional to X, where F is the restoring force, right? So, as we have seen over here, the simple harmonic motion system is basically in such a way that F is in the opposite direction of its displacement X. So since F and X are in the opposite directions, we can say that F is equal to minus Kx, where the minus sign denotes that they are in opposite directions, and K is the proportionality constant. Alright, so if the mass of the bob in this pendulum over here, if the mass is m, so we could say that F over here is basically ma, right? And this minus kx can be written down as x minus kx. Okay, so acceleration, right? Acceleration can be written down as the second derivative of the position function, right? So we write it down in this format. And we can, of course, divide both sides by m, right? So in physics, we say that this thing over here, k over m, is defined as the square of the angular frequency. So we can write this down as, and if we take this thing into the left side, then we are left with this, and this is the general equation of any system revolving in simple harmonic motion. But we actually want to simplify this entire thing. So what do? As you can see over here, this entire function over here can be written down as acceleration, right? This entire thing is the second derivative of the position function, and acceleration is basically the second derivative of the position function. And then again, acceleration can be written down as the first derivative of the velocity function, right? So we can write this entire thing down over here as dv dt plus omega squared x is equal to 0. And then again, following the chain rule of calculus, dv dt can be written down as dv dx times dx dt, right? And then again, notice that this dx over dt, dx dt can be said to be v, right, which is velocity. So we write this down as dv dx v plus omega squared x is equal to 0, right? And we multiply both sides with this x over here, and we are left with dv v plus omega squared x dx is basically 0. And if we take this thing over here to the right side, we are left with this. And we want to integrate both sides. And by integrating, we are left with, and c is the integrating constant over here. Notice that when we dealt with the pendulum over here, at the maximum displacement, which is x is equal to amplitude, the velocity of the bob is basically 0. And putting v is equal to 0 at x is equal to a, in this equation over here, c happens to be half a squared times omega squared. And then we are left with half v squared is equal to minus half x squared omega squared plus half omega squared a squared. And we can cancel the 2's in the denominator off, and we are left with v squared is equal to omega squared times a squared minus x squared. And by taking the square root of both sides, we are left with V is basically equal to omega times root over a squared minus x squared. But this is the velocity, right? We want to calculate the equation that says its position, right? So then again, we can write v as dx over dt, but we take the dt in the right side, and thus we are left with this equation, right? And then we get to integrate both sides, but integration would be easier if we took this term over here in the left side, because this term over here contains x. So we do that, and we have that this is basically dx over root over a squared minus x squared is basically omega dt. And by integrating both sides, we are left with this is sine inverse of x over a, and this is basically omega t plus the integrating constant phi, which we will later define as the phase constant. Alright, so by taking the sine of both sides, we are left with x over a is basically sine omega t plus phi, and by taking the a over here, we are left with x is basically a sine omega t plus phi. Well, what really is this phase constant? Well, the phase constant over here defines the displacement of the particle in simple harmonic motion from zero displacement, or the position of equilibrium initially. So, well, this is the equation for a particle in simple harmonic motion. Well, that's all.